All right, let's prove the min-max theorem. We'll call this min-max theorem proof. This is actually my second attempt, so let's just get to business. So first we'll state the min-max theorem. So we'll do min-max theorem. So the min-max theorem states, for a function f that is continuous within the closed interval ab, there exists an L and a U within AB such that f of L is less than f of x is less than f of U for all x within AB. Okay? We can draw the picture. Like this. For a function like this, we'll say, where this is a or this is b, and this is a, we see that this will be our u, and this will be L, and this will be our f of u, and this will be our f of L. Okay, so how do we prove this? We prove this by proving the following lemma. Okay? We prove the lemma, and then with the lemma, we prove the min-max theorem. The lemma states, for a function f that is continuous within AB, there exists a c that is positive, very important, right? The c that is positive, such that negative c less than or equal to f of x less than or equal to c. Intuitively, we can write this up as the following. We have a function. The function is like this. There is a c, and then there is a negative c. Okay? And the negative c is like this. We'll say this is c, and this is the c here. So no matter what x we put, and we can say this is the a and this is the b, it doesn't matter. To be fair, we can put this to be our b and this to be our a. It doesn't matter. But anyways, we can put a c no matter what x we put. We can find a c that is bigger than the function value there. In other words, it is bounded. Okay. How do we prove this? Well. So the proof is the following. First, we do a case, proof by case. So the first case is we'll prove the right-hand side. Okay. We prove that this is the upper bound. So in other words, this is the upper bound. Okay. We do a contradiction. This will help us. So instead of proving that there is an upper bound, we prove that for all c less than or equal to 0, there exists an x within AB such that f of x is greater than c. The negation of the upper bound is that for all c, we can choose an x within AB such that f of x is greater than c. Yeah, so no matter what c is, we can always find a bigger x. That is the principle. Okay, so how do we disprove this? How does this lead to a contradiction? Well, if this is true, we construct a sequence that is the following. We call this xn, such that xn is always greater than n. Okay, so if n is equal to 2, f of x subscript 2 is greater than 2. How do we know this is true? Well, we know this is true because f of x is not bounded above, so this has to be true. This could be squared, this could be whatever, but we know that this is true. We use the Bolzano-Weierstrass theorem to construct a subsequence, which we'll call this, such that the sequence is finite, converges, within the closed interval. Another thing we can state is that f of x and k, which is our subsequence, has to be less than the subscript. But as we know, this is also less than this. In other words, when we put in the subsequence inside the function f, we know that it is always bigger than n. Now we write that fn of L, which is the limit of the subsequence, is equal to f of the limit of the subsequence, which is equal to the limit like this, or by continuity. We know, by the way, this goes to infinity. We know that this is greater than the limit as n goes to infinity. This goes to infinity, which is a contradiction, because f of L has to be a finite value. Thus, f is not continuous, but f is continuous, which leads to a contradiction. For the case 2, for negative c less than this, we draw the following graph. We have this. We draw this graph. Suppose this is our function f. We have now found a c such that this happens. If we now take the negative of this c, it is a possibility that this c is not the lowest. It does not bound the function f beneath, you know? All right. So we have another case. So the case A is that this is the lower bound. And that means we're down already, because this is exactly what we want to prove. The other case is that this is bigger than f of x. Right, so the question is, what value of c do we choose now? So the observation we do here is that we rewrite this as being negative f of x. We do this being not strictly equal to. We do negation on both sides in positive, so it means that this is less than or equal to c. We call this g of x. So if this is the case, we choose new c such that negative c less than or equal to f of x. And we know that negative c is greater than or equal to c. I guess we choose a new c, we'll call this star here. So we choose negative c star. We know that this is like this. Thus we know that c is greater than this, right? Thus we know that the new c, we know that negative of c star is less than all z, and we also know that c star is also greater than c. Thus we can draw this picture. Thus we conclude that we've proven the entire statement. So now we prove min max theorem. Okay, we do another proof by cases where we prove f of x less than or equal to f of u. Okay, so we draw a picture for intuitive understanding, like we did before. We use the fact that we proved the lemma. So first of all, we use lemma to know f is bounded. Okay, what we do here is we construct the set S, which is equal to f of x for x within AB, we know by completes the axiom. By the way, let's draw this first. So let's do like this. So this is A, and this is B. We know that negative C, and we know that this is C. Like this. We know that there's a upper bound, which we'll call L. Supremum of S exists, and we call this L. Now we need to prove that there exists a U such that f of U is equal to L. Okay. Well, to do this, we define the sequence. We call this xn for n is equal to 1, with the property that f of n is less than L plus n, like this. And we do the other side like this. And this we know is true based on the supremum. Everything above here, this is L plus a half, maybe a half, something like this. And here, this is L minus a half. And we know that this is true. And we also know that there is an x between the points we can choose. Okay. By the Bolzano-Weierstrass theorem, again, we know that there exists a sequence like this that is has a limit, which is such that the limit as k goes to infinity of x and k is equal to a number we'll call little u. What we do now is we do the squeeze theorem. So by squeeze theorem, we know that the limit of L minus n is equal to the limit of L plus an, which is equal to the limit of fxn k, which is equal to L. Okay, we know that this can be written as f of the limit. This is k here. K goes to infinity, k goes to infinity, k goes to infinity, k goes to infinity, of x and k, which is now equal to, as we stated here, these two are equal, which is equal to f of u, which is equal to L. Okay, so this is pretty good. Okay, we prove case 2. This is very similar like the previous lemma. So we need to prove that there exists a L like this. And we can also note that now we know that the supremum, now we know that L is also within the function. Bolzano-Weierstrass theorem says that this is within A, because our function here is also within AB. Now, to prove this case, we do the very similar thing like we did before. We state that this is equal to negative, like this. We define this as being g of x, g of L. By previous case, we know L exists. Which concludes the proof. Thanks for watching.